Get ready for a marathon. Section 21.8 is big. This section is on the preparation and the reactions of acid chlorides. Also called acyl chlorides, also acid halides. It doesn't have to be a chloride. It could be a bromide, but your textbook just uses chlorides exclusively. So in the previous section, we looked at the carboxylic acid derivatives. Just in case you forgot, the acid chloride looks like this. We looked at the relative reactivity of the derivatives and learned that this guy is the most reactive out of all of the derivatives for a couple of reasons. One being that the chlorine, because it's very electronegative, it helps to increase the partial positive charge on the carbonyl carbon by drawing electron density away from the carbonyl carbon. And also, when we looked at the mechanism for the reactions that we're doing in chapter 21, these are nucleophilic substitution reactions, where we are substituting the chlorine, in this case, for this molecule. We're substituting the chloride for some other nucleophile, and the chloride is an awesome leaving group. So those two factors together, chloride is a great leaving group, plus chloride increases the partial positive charge of the carbonyl carbon, making it more attackable. Both of those things together make the acid chloride the most reactive out of all of the derivatives. And what that means for section 21.8 is that there's a lot of reactions that the acid chlorides can do, like a ton of them. So we're going to go through all of them. And most of them we're not going to learn the mechanism for, only a couple of them. First thing that we're going to look at just is the preparation, like how would you make it? And there are many different ways to make an acid chloride, but the easiest way on paper, the way that is most commonly used, is to start with a carboxylic acid and use this molecule called thionyl chloride, SOCl2, and this just replaces the carboxylic acid's OH group with the chloride. If you're curious, if you want to know about how this magic works, your textbook has the mechanism on around page 1006. So the book that I'm using has it on 1006, but if you have a newer book or an older book, it might not be exactly there, but somewhere in that ballpark, if you are curious to see the mechanism. That's the one way that we're going to use for preparing acid chlorides in this class on paper. Now let's get into the many different things that acid chlorides can do. First reaction, hydrolysis. As you can guess from the name, hydro referring to water, this is where we react the acid chloride with water, H2O. And because this is a nucleophilic substitution reaction, we are going to be replacing the chloride with our nucleophile, which in this case is an OH group. The mechanism for, if you're curious, the mechanism for this reaction is also on the same page or around the same page. You will see with the hydrolysis reaction, this reaction is done in a solvent such as pyridine. That's pretty common. Pyridine can sometimes be abbreviated just PY. Pyridine is necessary solvent for this reaction because it is a good base. It's basic. The potential byproduct of this reaction is hydrochloric acid. So the job of pyridine or something like pyridine is to suck up any hydrochloric acid that's coming off of that molecule during the reaction. We have a similar reaction called alcoholysis. And the alcoholysis reaction, The only thing that's different here is that we are using an alcohol as our nucleophile instead of water. So our nucleophile that actually ends up replacing the chlorine is an OR group. Let's put a prime on that R, and let's put a prime on that alcohol's R. And actually, I want to draw this alcohol a little bit differently. I want to change the location of that bond, ROH. And let's highlight this. The OR group from the alcohol is what actually ends up on the carbonyl group. This mechanism in reaction in general is really similar to hydrolysis, so you need to use a solvent such as pyridine for the same reasons. Next up, we have ammonolysis. So you can guess from the name that this time we are going to be reacting our acid chloride with an amine, such as NH3. It's a little guy. And in this reaction, we will be replacing the chlorine with an NH2. You know what I'm going to do? I should have thought of this in advance. I'm going to write my amine a little bit differently. NHH. I'm going to write it like that so that I can show you which parts of it are actually attaching over there. So one hydrogen, just like with the alcoholysis, one of the hydrogen atoms of the amine is not coming through to the product. This reaction also needs a base like pyridine, same as alcoholysis or hydrolysis. However, NH3 is a perfectly suitable base. So instead of putting pyridine in this, we're just going to have a lot of the NH3 molecule. You could see it written as excess NH3, and you could also see it written as 2NH3. Same reason. That extra NH3 is just being used to absorb HCl that is being produced. Now, we can do this reaction also with a primary amine. So that's notation that we really haven't used yet, but a primary amine is going to have one R group on it instead of having 3 hydrogens on it. And with a primary amine, we're going to get an amide with one R group on it. And let's highlight our amine. We can see how much of it comes through into the product. And again, we're going to need to have excess of this amine to absorb HCl. And then last but not least, we can do this reaction with a secondary amine. This one's got 2 R groups on it. We're going to need excess of that, so put a 2 there. And here we are going to be producing an amide that has no hydrogens at all on the R group. No hydrogens at all on the nitrogen. That's what I meant to say. Only R groups on the nitrogen. So there's ammonolysis. Next reaction that we have, reduction to an alcohol. This one is going to feel familiar. We haven't actually seen this reduction yet, but it is with our good friend LAH. We're going to use excess. We're going to look at the mechanism for this, followed by the usual H2O or H3O plus. And this is going to make an alcohol. And I need you guys to be careful when you're doing this reaction. Don't lose your carbonyl carbon. Make sure that you keep that carbonyl carbon in your product. Let's take a look at how this magic happens. You should feel pretty comfortable with LAH mechanisms because we have been looking at them for a really long time with a variety of different carbonyl compounds. Remember that in LAH reduction, your actual nucleophile is the hydride ion H-, and that hydride ion is attacking the carbonyl carbon and opening up the carbon-oxygen double bond and giving us a single bond to oxygen, a chlorine still there, and we have this hydrogen that we've added. And if you refresh yourself back to, I think it was section 21.7 when we were looking at the generic mechanism for this process, the next thing that's going to happen is closing that carbon-oxygen double bond and kicking off a good leaving group. And on our carbon, the best leaving group is the chloride, so that's what's going to go. And look at what we make. Our friend, the aldehyde. Aldehydes are very reactive towards the hydride reagent. So a second hydride is going to come in and react whether we want it to or not. The second hydride is going to come in and it's going to react again by attacking the carbonyl carbon again for a second time, open up the carbon-oxygen double bond. This time we have something that looks like this. Now this time, at this particular point, we are not going to see the carbon-oxygen bond forming again because none of the things on here are good leaving groups. Those are all really terrible leaving groups. So the carbon-oxygen bond is not going to come back because we don't have any sort of anything that resembles a good leaving group. So here's where the reaction just kind of stops until you put some water in there or some acid in there to protonate and give you the alcohol, the product of this reaction. It is possible for us to reduce an acid chloride to an aldehyde, like if we only wanted it to go this far and stop and not continue. We can do that, but we have to use different reagents for that process. For the reduction to an aldehyde, the reducing reagent that we use for this is awesome. It is lithium, aluminum, put it in square brackets, tritert butoxy. So it's the tert butyl group, which is OCCH33. We've got 3 of those. Hydride, lithium, aluminum, tritert butoxy hydride. It's a lot to say. And step 2, just like normal, step 2 is water. So this is, like, you're familiar with this tert butoxy group. That's our bulky base that we use when we're trying to do certain types of elimination reactions. This hydride reagent, because of its bulkiness, and that makes it very difficult to react, it will react with the acid chloride and turn it into an aldehyde, but this lithium aluminum tritert butoxy will not react with aldehydes. The aldehydes are not as reactive as acid chlorides, and also the lithium aluminum hydride the lithium aluminum tritert butoxy hydride is also not as reactive. So this is how we would be able to turn an acid chloride into an aldehyde. And then we only have 2 more. Reaction with Grignard, which we're already familiar with, although I don't think that we've done it with an acid chloride before. But it is going to work the same way as other carbonyl compounds. This time, we are going to draw the mechanism for this. You do need to have excess of your Grignard. I'm going to call it R prime MgBr, And then remember, the Grignard reaction is has a step 2 H2O or H3O plus. The Grignard reaction and the hydride reactions are very, very similar, almost exactly the same. So we are going to be putting 2 R groups from the Grignard onto the carbonyl carbon. Let's highlight those R groups right there, right there, right there. And let's look at the mechanism to see how this happens. With our Grignard reagent, the actual nucleophile is an R minus, a carbanion, and it is going to attack our carbonyl carbon, open up the carbon-oxygen double bond, and we make, oh, I want to change my R minus, I want to change it to an R prime. We make this guy right here, and this molecule, our typical mechanism for nucleophilic acyl substitution, the carbon-oxygen double bond wants to close back up and it wants to get rid of a good leaving group. Look at what's on this carbon. We do have a good leaving group, so we'll go ahead and get rid of that chloride. And that leaves us with a ketone. And ketones are very reactive towards Grignards. So that means that we're gonna have another Grignard, another R minus attacking the carbonyl carbon, and we can't prevent this from happening. This reaction is just gonna happen so fast that like putting only one equivalent of Grignard in is not gonna be able to keep this from happening. So you just have to roll with it and give it lots and lots of Grignard so that it can fully react. Now we have 3 R groups on our carbonyl carbon. 2 of them were put there by the Grignard. Just like with the hydride reaction, we're not going to see that carbon-oxygen double bond closing back up because we don't have anything that even remotely resembles a good leaving group. So it's just going to stay like this until we bring in our water or weak acid to protonate the O minus. And we are left with an alcohol with 2 new R groups on it. And just like we saw with the hydride reaction, we do have a way to do a Grignard-ish reaction that goes only to the ketone. So it's like partially reacting, and this uses a reagent that is similar to a Grignard, but it is not as reactive. This type of reagent is called the reagent is called a lithium dialkyl cuprate, which is a very fancy sounding name. So here we're going to take our acid chloride, and the reagent that we're using is a dialkyl. That's where that part comes from. So 2 R groups, and I'm going to make them R prime. A copper for the cuprate in the name, and a lithium. And this is just in one step. There isn't any kind of follow-up H2O. And this converts our acid chloride to an aldehyde by just pure magic. And so that's a lot of reactions. But remember that acid chloride does the most. So this probably feels a lot like the end of 241 when you were learning all the reactions of alkenes and alkynes. It felt super overwhelming. There is a really great resource in your textbook. So it's figure 21.9. It's going to be around page 1010. And it's also, the figure is going to be repeated in your textbook at the end of the chapter. It is in my textbook. The second time, it is on page 1034. In there, it is under the review of reactions. This figure is like a starburst roadmap of all of the reactions of acid chloride. So it's got an acid chloride in the middle, and then it's got 7 million reactions coming off of it of every single thing that the acid chlorides do. And it also includes reactions to make acid chloride. So it has everything on it. And this is a great resource for doing problems that involve reactions of acid chlorides.